All right, so today we're going to start in lesson 1, looking at real numbers and number operations. Real numbers are basically any number you know at this point. Some of you might know a number that's not a real number. It's not part of our Algebra 1 curriculum, but if you came from another school, you may have encountered this number that is not a real number. But it is likely that all the numbers you know we can classify as real numbers. Our whole numbers start at 0 and then count up. They do not have decimals or fractions. They do not include negatives. The integers expand that to include negatives, but still no decimals or fractions. The rational numbers are any number that can be written as a fraction, even if it's not written that way, that it could be written as a fraction. So 2 is a rational number, because I could write 2 as a fraction, 2 over 1, 4 over 2, right? So there's ways that I could express that as a fraction. 0.5 is a rational number. Even though I gave it as a decimal, I could write it as 1/2. So it could be written as a fraction. So if I can write it as a fraction, it's considered rational. If I cannot write it as a fraction, then it is considered irrational. Those numbers seem less common to us, but there are theorems in math that tell us that they are really just as common as these other types of numbers. We just maybe don't work with them as often. They don't seem as pretty to us, but there are still lots and lots and lots of them. One of the most famous kinds of those numbers is pi. My font kind of got messed up, so it's there, but it's just up in the middle of the words. But pi is a really common irrational number. Irrational means there's no way I can write that as a fraction. Sometimes we try and say that it's about 22 over 7, but that's not perfect. That's not exactly what it is. Pi goes on forever and ever and ever without repeating itself and without ending. The square root of 2 is an irrational number, or any other square root that we can't take nicely. So the square root of 3 is irrational. But the square root of 4, that one I can take nicely. That's 2. So that one's rational. Okay? If the square root we cannot take nicely, it's irrational. Questions on those? On the test, you will be asked to classify numbers according to all of the classes in which it belongs. So a number can belong in more than one of these classes. So like if I give you the number 5, the number 5 is lots of these things. 5 is real, because I've heard the number 5 before. It's whole. It is not an integer. Oh yeah, sorry, it is an integer. I don't know why I said that. 5 is an integer. And it's rational, because I could write it as a fraction. 5 over 1 or 10 over 2. Those are ways to write the number 5. Okay? So that belongs in a lot of classes. I could ask you about the number -7. -7 is real. Is it whole?
No.
No, because it's negative, and whole isn't negative. It's an integer, because integers can be negative. And then is it rational or irrational? It's rational, because -7 doesn't go on forever. It's just -7. Okay? Irrational is a decimal that goes on forever and ever and ever without starting to repeat itself like pi. All right? All right, so in our first type of problem here, we're asked to graph these numbers on a number line. A number line should have arrows at the end because it goes on forever and ever and ever in both directions. Positives going off to the right, negatives going off to the left. I always like to place 0 on my number line, even if it's not one of the numbers in the problem. It just kind of gives some perspective. It doesn't have to be right in the middle, though, because it goes on forever and ever, so we could be looking at any snippet of the line. But I like to put 0 on there. Then we want to put these numbers in order. Now the problem with putting these numbers in order is that they're kind of different. So it's kind of like comparing apples and oranges. So I think the easiest way to compare them is to make them all the same type of thing. So if we express them all as decimals, then we'll be able to tell how they line up. So what is 4/3 as a decimal? 1.3333 forever and ever and ever. Square root of 2, you might not know as a decimal, but you can just grab a calculator and type that in, and it's about 1.4 something, something, something. And then 2.7 is already a decimal. Okay. So then we can see how they line up, and we can see they were actually already in order. Now when you make your final answer, please use the numbers that were actually in the problem, not the decimals that you created to compare them. Okay? So in your final answer, and you'll have some problems like this in your homework, please write them as they actually appeared in the problem. So as 4/3 and as square root of 2, not as the approximate decimal that we used. Okay? I don't care about spacing, so yeah, 4/3 and square root of 2 are a lot closer to each other than square root of 2 and 2.7, but I don't really care about that. All I'm going for is just get them in order on the number line. Okay? Questions?
How do you get square root of 2 to the decimal?
Just type it in a calculator.
Oh, okay.
Yeah. There's actually 2 different problems here. So it's like a part A and a part B. So go ahead and try these. Put the numbers -2 and 3 on a number line, and then put the numbers -1 and -3 on a number line. So arrows on both ends on the number line, because it does go on forever both ways, to infinity and negative infinity. I like to throw 0 on there to give some perspective of where the true center of the infinities is. And then negatives go on the left, and positives go on the right. Again, I don't so much care about spacing, so yeah, 3 is further away than -2, but just get them on there in the right spots, and I don't really care about measuring out the spaces. If you do, that's awesome. If not, that's fine too. Just get them on there in order. For the next one, -1 and -3 are both negative, so they're both going to go on the left of that 0, and then we have to be careful with our negatives that we make sure that we're counting kind of backwards. -3 is smaller than -1. Okay. Questions? These are some properties for us. These properties are important to know by name when it comes to the test. They will be tested by name. I'll give you an expression like we'll have in our next examples, and you'll need to name what property it is. When we name properties, we need to use 2 words. We need to name the property's name itself and which operation it is being applied to. An operation is something we do to numbers, like addition or multiplication or exponents. Something that we do to a number, we're naming that kind of arithmetic. So we need to say that it is whatever property name, but then also either addition or multiplication, what's happening in that property. Closure doesn't have anything in the boxes here because it's kind of hard to express with a formula what closure is. Closure just means that when you do it, you're not going to get anything totally new and different outside of that class. So if we're talking about real numbers here, that means if I add a real number to a real number, I should get another real number. Or if I multiply a real number by a real number, I should get another real number. Since pretty much everything you know at this point is a real number, we can be sure that that's kind of a safe thing to do. The commutative property says that things work backwards and forwards. So a plus b is the same as b plus a, or for multiplication as well. The way that I remember is I try to think about what that word sounds like. So when you hear commutative, a lot of students put an N in there. If there's no N, it's just commutative. What word do you hear in there? Think about driving. Commute. Okay, so it kind of starts with that word commute, which is like your morning commute going to work or school. It's the drive that you take. And what I think about with commutative is that when I drive to school and when I drive home from school, I'm doing the same thing but backwards. Right? I don't have any one-way streets. So if you live in like a one-way street area downtown or something, it doesn't quite hold up. But I don't have any one-way streets. So when I drive to school and I drive home from school, I'm doing the same exact route, the same number of miles, I'm just doing it backwards. But it's the same journey. Okay? So that's what our commutative property says, that we can do the same thing backwards and get the same answer. The associative property says that we can move parentheses around in the problem, and it won't change anything as long as it's only the same operation going on in there. So if all we're doing is adding, it doesn't really matter where the parentheses are. Or if all we're doing is multiplying, it doesn't matter where the parentheses are. What word kind of sounds like associative? Associate. So who do you associate with? Or a lot of lawyers' offices are like so-and-so, 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 and associates, right? So it's a group of people. Associate is like a group of people. And so what we're doing here is changing the grouping. So we're moving those parentheses around and adjusting the groups, but getting the same result. The identity property says that there's a way to keep numbers the same. So for this, I like to think about what is your identity? And a lot of people place their identity in the wrong thing. So, and I'm here as well. That's still daily. I have to remind myself what my true identity is. I think of myself as a mother first a lot, because my kids are really important to me. Or I think of myself as a teacher first, because I love my job and I love what I do. Or I think of myself as a wife. And I am, and I try to be a good one, and that is really important to me. But my true identity is that I'm a child of God. And that never changes. And so the identity property is a way that we can keep the numbers the same, that they won't change. Because my other identities might change. There might come a time when I don't teach anymore for some reason or another. There might come a time that God chooses to take my children away from me, and then I wouldn't be a mother anymore. Or there might be a time that I would lose my husband for some reason, and I wouldn't be a wife anymore. And if that's where I'm placing my identity, my world will crumble if I lose that. So we need to make sure we're placing our identity in the right thing, and that's something that will never change. I will always be a child of God, and the identity property tells us that we can stay the same forever in that. Okay? The inverse property is what gets us that identity value. So when we add, we can add the opposite thing to it. So 2 plus -2. When we multiply, we can multiply by the fraction of it. So 2 times 1/2 would get us to that identity value. Then the distributive property is the one exception to needing to state an operation because it uses both. The distributive property uses both multiplication and addition, and it talks about passing things out. So at the beginning of this lesson, I passed out papers. I gave, from my stack of papers, 1 set of papers to each person. And that's what the distributive property does, is it takes that value that's being multiplied and it gives it to everything in the group. So everybody in this group, in this class, got that set of papers, and that in this property, that A is passed out to everything inside of that group. Okay? Questions on any of these properties? All right, so in our problems, we'll be asked to identify the property, remembering that we need to use 2 names, both the property name and the operation that's happening. So in the first one, what property name is that?
Associative.
Associative, because what we're doing is moving around parentheses. You can abbreviate, just make sure you use 5 letters, please. And what operation are we doing?
Addition.
Addition, so we'd say associative of addition. You can use a plus sign if you want. I don't care as long as I can tell what you mean. But we need to both give a name of the property and the operation that it's doing. Second one, what is that one?
Identity.
Identity, because it's staying the same. So that's the identity, and then we say of multiplication. And again, you can abbreviate if you want, as long as I can tell what you're talking about. So you could say ID, identity is fine. What's the third one doing? Commutative. It's the same thing but backwards. So that's the commutative of addition. And what's that last one?
Inverse of multiplication.
The inverse of multiplication, because it's getting us to that identity value of 1. All right?
Wait, what was the last one?
Inverse of multiplication. Questions? terms for us here. Opposite is what we call the additive inverse, or it means it has a different sign to it. So 2 and negative 2. 3 and negative 3. Every number has an opposite. You just throw a negative in front of it, or if it already has a negative, you take the negative away. Okay? It's what we add to each other to get that identity value of 0. A reciprocal is a multiplicative inverse. I like that word, multiplicative. It means that when we multiply them, we would get that identity value of 1. It's the same as flipping it upside down. Every number has a reciprocal. What's the reciprocal of 2/3? 3 halves. We flip it upside down. What's the reciprocal of 1/5? 5. 5 over 1, or just 5. What's the reciprocal of 3? 1/3. We flip it upside down. There was nothing to flip upside down, so we put the 1 there. Okay? Every number has a reciprocal, and it's just flipping that fraction upside down. If it's not a fraction, make it a fraction. In these, we want to evaluate the expression. Means we need to know some terms in these problems. Always take the numbers in the problem in order as well. So the first problem asks us to find the difference of 7 and negative 10. What does difference mean?
Subtraction.
Subtraction. So we're going to do 7 minus negative 10, which is 17. Double negative makes us add. I lost something in my notes here on the sign, but it says the quotient of negative 24 and 1/3. What does quotient mean? Divide. So we're going to do negative 24 divided by 1/3. How do I divide by a fraction? Multiply by the reciprocal. So we're going to flip that over and make it a 3.
Negative 72.
Multiply those, and we get negative 72. The sum of negative 3 and negative 15, what does sum mean?
Addition.
Addition. So negative 3 plus negative 15?
Negative 18.
18. The product of 2 and negative 8, what does product mean?
Multiplication.
Multiplication. So 2 times negative 8
Negative
is negative 16. Okay, so make sure you know what those 4 words mean. And always make sure you take the numbers in the problem in the order they come, because sometimes it does make a difference. So like on that first one, if you subtracted those backwards, you would have gotten a different answer. So make sure that you take them in the order they come. Our last set of problems here is looking at units and operations. We can only add and subtract if the units are the same. So I can't talk about like taking 3 gallons and adding it to 4 hours. What does that mean? Like, how am I taking 3 gallons of gas and putting it together with 4 hours of time? It doesn't make any sense. So we can't add things if they are different units. Okay? So when we are adding or subtracting, we need to make sure we're talking about the same type of unit. I can do 345 miles minus 187 miles. Then I could be talking about some sort of distance. I need to go 345 miles. I've already gone 187 miles. So how much more do I have to go? That makes sense, okay? But they have to be the same units. So if we subtract those values, we get 158. Feel free to use calculators for arithmetic. I do, okay? It's fine to do that. And then we need to give a proper unit with our answer. And the only unit we're dealing with here is miles. So it's still going to be in miles. We can multiply and divide when units are different. That's okay. We cannot add and subtract, but we can multiply and divide different units. So I can multiply 1.5 hours by 50 miles an hour. We can make everything into a fraction, and we can cancel units that match on top and bottom. Then I can do my multiplication. 1.5 times 50 is 75, and what will the unit of my answer be? Miles. So what this problem is talking about is something like, I drove for 1.5 hours at a rate of 50 miles an hour. How far did I go? 75 miles. Okay, so that would be an application of what these numbers would mean. We can divide when units are different. Even if we can't cancel them, it's okay to divide them. So when we divide these units here, we divide the numbers, and we get 8 in our unit would be dollars per hour, because we can't cancel them, so they're both going to be there. An application of this problem would be, I babysat for 3 hours, and the people paid me $24. What were they paying me per hour? $8 per hour. And our last one here is something that's called a unit conversion. We're starting out with 88 feet per second, which is a rate of speed. But it probably doesn't mean anything to you. Like if I said I was going 88 feet per second, you're like, awesome. Were you walking, running, driving a car? Like to me that means nothing because we don't work in meters. We work in miles. So I don't really understand meters. So if somebody says 88 feet, or feet in this problem, feet per second, it doesn't mean anything. I have no clue if that's fast or slow. So what we want to do is change it into something that makes sense to us, like miles per hour. So we can do conversions and say that with feet, if I want to change those into miles, there are 5,280 feet in 1 mile. And you don't need to memorize these conversions, they're in your book. But that's how many feet are in 1 mile. Seconds are good. We talk about seconds, but when we're thinking about speeds, we're usually thinking of per hour. So if I turn those seconds into hours, there's 3,600 seconds in 1 hour. 60 minutes of 60 seconds gives us that hour. So we can cancel out our matching units. Seconds cancel seconds, feet cancel feet, and then we can do our arithmetic. We will multiply anything on the top and then divide by anything that's on the bottom. So in our calculator, we would type in 88 times 3,600 divided by 5,280. And that gives us a result of 60. Our units are whatever's left over when we cross the other stuff off. So that'd be miles per hour. So now 60 miles per hour, I understand that I was not walking or running, I was driving. Okay. So that gives some connection to how fast this is going. I do this a lot when I watch the Olympics, the Summer Olympics, particularly with track and field. So I like to see when they do the sprints, like obviously Usain Bolt is really fast, but I don't really have a concept unless I'm like sitting in front of him, watching him run by me of how fast he's really going. So I like to say, okay, he did the 100 meters and however many seconds he did it, and then I like to turn that into a miles per hour and figure out how fast he was actually running, and that has a whole lot more meaning to me then. I can say, wow, he really is running fast.
What is
Ooh, I'd have to look up the data from the last Olympics. I want to say it's like over 35 miles an hour average. Which means since he started at 0, at some point he was going faster than that, right? I don't know how long it takes him to reach his peak speed or if he's constantly accelerating. But it's fast. I don't remember if it's like 30 miles an hour, 35 miles an hour, something like that on average.
30.
I don't know. I remember when I did the division, I was like, I thought it was impossible. I remember thinking it was ridiculous. But it's only 100 meters, right? So at least he doesn't have to keep that up for very long, but still. So, all right, that's it. So your homework is from lesson 1. Make sure you pay attention to where there are commas and where there are dashes. That if it's a dash, you're doing all the problems between there, and if it's a comma, you're just doing the list of problems.